There, Algebras. Welcome to your Chapter 11 Lesson 8 notes on transforming quadratic functions. So today what we're going to do is we are going to take our parent function, and we'll call it f of x equals x squared, and we are going to move that parent quadratic function up and down and my left and your right, and we're going to shrink it, like narrow it up, and we're going to widen it, and we're going to flip it upside down so that it's a frowny face parabola, and we are going to look at how we can manage to do all of that in the form of our equation. And so how does the look of the equation change based on the movement change we want to accomplish? Now, we talked about all of this stuff back in Chapter 3, Lesson 7, I believe. And when we were doing that there, we used this general form of the function that would get changed. Well, I will call that back to us, and we will change the actual function equation for our quadratic functions. So we'll kind of do a little bit of both. So we'll have that function notation, and we'll have the actual form of our quadratic being changed to accommodate what's the movement we want to make from our parent. So our parent function, the function we're basing all these movements off of, is just y equals x squared, or what we would call f of x equals x squared. And the reason we'd like to call that f of x equals x squared is because if we have that f of x notation, that's what we can make the general form function changes to. And so we don't necessarily also change the equation, although I will teach you how to do that. So we'll be able to look at the function notation change as we go. So what I'm going to do is I'm going to turn my graph table function or my graph table mode on. And in y equals, I'm going to graph my x squared, my parent function, so that I can have a peek at what this looks like. Now, second in graph, of course, takes me onto the table where currently my ninja star is right on my axis of symmetry and vertex, okay? And let's arrow up so that we can center that in our table on our page. But that 0, 0 is my vertex. Also happens to be my root. Also happens to be my y-intercept. So it is the plethora of all the things that I kind of look for in a quadratic function when I graph it. Okay. Well, our same picture right here. We have been dealing a lot with standard form of our quadratic functions. Y equals ax squared plus bx plus c. And that's where we have to have an a present because we have to have an x squared present. Of course, that makes it a parabola. And the way to find the equation of our axis of symmetry is x equals negative b over 2a. Pulling our b, changing its sign, taking our a, multiplying by 2, and seeing if that's a fraction that we can simplify. Vertex form is something that we have looked at a couple of times, but not as in depth. And vertex form actually, in its function equation, has an a value in the front that's the same as this a value. It tells me the direction my parabola is going. So if this a is positive, well, then I have a smiley face parabola. If this a is positive, I also have a smiley face parabola because it's the same thing. So, and if it's negative, frowny face parabola. Now, the h and the k in this form are actually telling me the x and y coordinates of my vertex. For the h, it's the opposite sign of what is inside those parentheses, is the x coordinate of my vertex. And for the k, it's the correct sign of what's outside of the parentheses, is the y coordinate of my vertex. So that's pretty cool. And notice that does not match up with anything in the standard form function equation. So those are two different looks at the same function. Okay, so two different equational looks of the same function. Now, today what we're going to really be doing and concentrating on is transforming our quadratics by widening them, narrowing them, flipping them upside down, moving them up and down, moving them left and right. Oh my goodness, why can't I get this right today? There we go. Okay, so that's what we're going to want to be doing is moving our parabolas around a little bit. So I'm trying to get no shadow. There we go. So we'll be moving our parabolas around a little bit when we're looking at this, okay? Now, I just want to show you, this is multiple types of changes in each of the scenarios. The middle of each of these is that y equals x squared parent function, and we are narrowing up, we are widening out, we are flipping upside down, okay? So when I'm talking about here is my original function, y equals x squared, when you multiply the front of your x squared by something, let's say an integer, it will narrow up. So all of a sudden, y equals 2x squared. Let's try that, see what that looks like. We leave our parent and we do y equals 2x squared. Look, that narrows me up a little bit. If I go to, okay, wait a minute, let's do a y equals 1/2 in front of the x squared. If I'm kind of dividing the front by 2, now we're a wider parabola, okay? And actually, it's even more if I do a bigger number like 3 for my multiplier or my divider. And now all of a sudden you see even narrower, even wider, right? Compared to your blue original function. What do we notice about multipliers in the front? Well, 0, 0 is still my vertex, my one root, my y-intercept, when I have that as the case. I'm only widening out the points around that parabola, or narrowing up the points around that vertex, okay? Now, what if I threw a negative in front of that? So what if I went negative x squared? Well, it's the same as when I throw a negative in front of any of my functions. If I have a negative in front, it flips it upside down, okay? And so these are a values that are less than 0. That's what this means right here, is when I'm under the x-axis like this, I have a frowny face parabola because I have a negative x squared going on. So that's kind of the multiplier, changing the a value and what changing the a value does for us. Let's talk about changing, and I'll get rid of all of these. Let's talk about changing the k value, the value that I add or subtract from the end in my vertex form of my quadratic. So if I look at adding to the end, so let's say I have x squared, but I want to add to it, let's add a 5 to the end, okay? What is that going to do? That actually takes my parabola and moves it up 5 on the y-axis. So that changes my vertex. If I go second in graph, now I'll get onto my vertex of my original parent function. It was 0, 0. That's going to change the vertex of the new function to 0, 5. Every point got moved up a y value of 5. So every y value got added 5 to it. And that's where all these new y values are coming from. So the adding that value at the back pushes up my whole quadratic. So if I subtract a value from the back, let's take x squared and let's subtract 5 now. If we look, what does that do? The whole parabola moves down 5. Okay, so it moved down 5. And so when I press second in graph this time and I look at my vertex, now my vertex went from going up 5, 0, 5, to now 0, negative 5, the other direction. So notice these y values, every single y value here is now subtracted 5. So they're all whatever your original y value was in your parent function minus 5. And that's how we get all of those points. That one is nice and easy because it's pretty straightforward. Okay. And then let's look at how we're going to notate moving left and right. Because I actually think this is the hardest part of this particular lesson in doing this with quadratics. So what we're going to do is we're going to actually use that vertex form to actually make those changes of going left or going right. So if I go in parentheses with my x, if I subtract, I'll say 5 again, because it gives me a really good picture of what's going on, in parentheses and square it, it actually moves the opposite direction we think it should. So we're going into the vertex form because we're changing the x value of the vertex. So now when I press graph to see it, look, instead of shifting to the left 5, because we subtracted 5 inside, we feel like it should go left 5. It doesn't. It moves right 5. So on second in graph, on my table of points and at my vertex, look. Okay. And again, because I was at 0 as an x value, my vertex is actually 5, 0. And so see what that did? That changed my x value by adding 5. Okay. All of those x values. And you think it should be the opposite because it's a minus 5 in the parentheses. But that goes back to what I said about vertex form. It's the opposite sign of what's inside the parentheses that determines your x coordinate of your vertex. So now if I look, the opposite of that, moving left 5, would be inside the parentheses saying x plus 5 in parentheses squared. So now when I press graph to see that, okay, that did shift the left 5 that I was looking for, or that I thought I should have seen. Okay, and so now I'm over here to a vertex of negative 5, 0. Second graph, let's just prove that's the case. Oh, probably don't want to move. I want to be right there. The negative 5, 0 should be, and look at that, there it is, negative 5, 0, right there. So that vertex changed my x value of it with that change inside the parentheses. Okay, that vertex change occurred inside the parentheses for my x's, and it's the opposite of what you think it should be. So, how do we put this into practice, and how does the Regents ask these types of questions of us? That's what we're going to be looking at today. All right, so I'll flip my page over so you can see, again, some of the changes. This was a little bit more exaggerated, the same types of changes that we were talking about on here, okay, so that we had on our graphing calculator. I'm going to clear out all of the changes that I made and just go back to having my parent function here and go back to being on my vertex so that you can see where I'm at. Okay. Now, let's generalize what these changes look like in f of x form. So in function form, let's generalize what the changes we made are going to be. Okay. So when we take our original f of x and we subtract k from the back, that means we are going down k number of places. If we add k to the back, that's up k number of places. Whatever that k value is. If it's 5, then we went down 5. If it's plus 5, right? If it's a minus 5 back here, we go down 5. It's a plus 5 at the end. We go up 5. Inside the parentheses negative is right k number of places, and that changes the vertex. And it's inside the parentheses is left if we add k. So that goes left k number of places. And what that does is that changes the vertex from that 0, 0 to negative k or positive k, depending on left or right. If you multiply by a negative in front, so your a value is a negative, then you are flipped upside down. Those are the frowny faces. So all the frowny faces have a negative in front of the x squared. And now what we're doing here is we're multiplying by the front, or multiplying by a fraction is what widens us out. And so if we multiply by a whole number, we narrow by that much. And if we multiply by a fraction, we widen by that much. So these are the function notations we have to be able to interpret. And we also have to be able to interpret multiple function notations at once. Okay, so that is the other piece that we're trying to kind of like focus in on. Okay. So how do questions like this get asked? Well, in exercise 1, this is actually a former Regents question that I did really like. I liked this Regents question. I thought it was pretty straightforward. It says, on the graph of the function, this is p of x. So here's p of x. Okay, great little quadratic. On the same set of axes, sketch the function p of x plus 2. Okay, now wait, I'll keep this handy. Inside the function notation, we added 2. So which of my notations should I be considering here? Inside we added, I should be going left 2 places. That's what that's saying to me. So let's take that and go left 2 places. This is my original function, p of x. So take the vertex to start and go left with it 2 places and drop your vertex. Now take the next coordinate point you can see right here and go left with it 2 and drop your next point. It ends up being the new y-intercept. Take this point right here, go left with it 2, drop a point. Now here's another coordinate right here. There's a root coordinate. Let's take that and go left 2. Let's take this root and go left 2. Okay, so things are lining up so far. Now there's another coordinate right here, another grid point right here. Go left 2 with it. Go left 2 with it. Okay, and that's plenty to show exactly what was happening here. And this, anything we put on the graph we label, including this, the only thing we know about its equation, it's p times a p of x plus 2. And we moved everything left 2. So this indicated to me that every point had to go left 2. We subtracted 2 from the x value of every single coordinate point on there. That's great, because that's former Regents question. So if we can do that, we're going to be great when it comes to this exam. Based on the parent function, f of x equals x squared, what are the transformations that occurred to give us this graph? Well, we know, and we've got it right here next to us on our graphing calculator, that our parent function, f of x equals x squared, has a vertex at 0, 0. So let's just consider this is what my original function looked like. To 2, 4 and negative 2, 4. Okay, so this is what my original function looked like. How did this function change? This was f of x. So what changes were made? Well, the first change made is we flipped upside down. So that means we're going to have a negative x squared now. Okay, so that's the first thing. That's the big one that I notice. The second thing I notice is if I just flipped this upside down and only multiplied the front by a negative, well, then my vertex would still be at 0, 0. And for this green function here, that is the movement, it is definitely not at 0, 0. In fact, it's at a positive 1, positive 5. We took care of the flipping part. So now when we're doing that, we are looking at, well, where did I go? Did I go left or did I go right with the vertex for that particular thing, right? Well, I went right 1 as an x value. So that means inside the parentheses, I'm going to be subtracting 1 because it's the opposite of what I think should happen. And then, lastly, I also went up 5 to get the y coordinate here. So that means at the end of the function, I'm going to be adding 5. So let's put all that together in function notation. If f of x was my original function notation, I have taken f of x and I've put a multiplying by 1, negative 1 in the very front. So a negative in the front. I need to subtract 1 inside the parentheses, and I need to add 5 outside of the parentheses, and this is the notation of my new function. Okay, so this is the changes that were made to make this new function. So notice I took them one step at a time. Okay, we have to be able to combine changes to think about them. So I took them one step at a time. Exercise 3. Did not give me a picture this time, so I'm kind of like flying without a picture. So in exercise 3, I want to know if the parent function is transformed to become f of x plus 2 minus 8. What are the two transformations that occurred to my original f of x? Okay, one at a time, right? So inside the parentheses goes the opposite direction you think it's going to. We added inside, so that's going to go left 2. Outside the parentheses does exactly what you think it's going to do up and down. So this is going to have gone down 8, right? So what are these two transformations? 1, we went left 2, and 2, we went down 8. Which means, by the way, that my new vertex, if this really was f of x equals x squared, my new vertex is going to be negative 2, negative 8, because that's where I'm moving the x and the y. Okay, last one, certainly not the least. We've got, based on the parent function, f of x equals x squared. Okay, so that's the one that's on our graphing calculator right there. What are the transformations that occurred to create this function? Also, write the quadratic equation. Oh boy, they're asking us to really reach on that one. All right, that's okay. Let's think about where the original was. The original was right here at 0, 0. We had points at 1, 1 and negative 1, 1 and 2, 4 and negative 2, 4. There we go. Okay, so now we did not flip this time. So we don't have to worry about that particular thing, but we did move. We can see that we moved that vertex to the right 2 and then down 4 to get our vertex to 2, negative 4. Okay, so let's think about the transformation movements. First, we went right 2. So that's x minus 2 in the parentheses. And then we went down 4. So that's negative 4 outside the parentheses. So if our original f of x was x squared, this is a change in the parentheses that makes the x squared. This is a change outside the parentheses that moves us up and down. And we'll do those both in the function notation changes and in the actual equation notation changes. So this is going to be f of x minus 2 minus 4. Those are my changes. So in the actual function change, it's going to be x minus 2 in parentheses squared minus 4 on the outside. And now that seems like a lot, since those are the changes I made to f of x, right? That seems like a lot. But what I'm going to do is just verify that in my graphing calculator. So I'm going down to Y5 to keep my color consistency, but I'm going to check to see if x minus 2 in parentheses squared minus 4 at the end really does give me going right 2 and down 4 for my new parabola. And sure enough, right 2, down 4, Let's press second in graph be on our actual. So I'm going from 0, 0 to, look at that, to -4 for finding those points. Now this one still did have a 0, 0 on it, just like ours up here. It had a 0, 0 on it. It just isn't the vertex anymore. Okay? And so those are the ways we have to apply this information. Okay? Is changing the function notation is the minimum. Being able to change this function notation is the minimum. The maximum I would ask you to do is to change that actual equation notation. Okay, last but not least, another former Regents question. Based on the parent function f of x equals x squared. Oh, there we go. We have it. Let me get rid of the green here. We are going to change this. So we're multiplying the front by -2, and then we are adding 4 at the end. So let's think about what those two changes that we are making actually make on our x squared, right? And because it wants us to write the quadratic equation to describe the new function. So what we can do is we can think about graphing the changes. So if your original function was still right here, 0, 0, 1, 1, and 1, and -1, 1, and 2, 4, and -2, 4, and 3, 9, and -3, 9. Okay, so if we want to think about those changes that are being made to our original parabola. Okay, right there. And again, whoops. There we go. Sorry about that. I wasn't paying close enough attention. There we are. Okay, if we want to make these changes, let's consider where this moved. So multiplying the front by -2 flips you upside down and narrows you. And adding 4 at the back means that your vertex is going up 4. So our vertex is going to go up 4. 1, 2, 3, 4. But now this vertex is a maximum. And so instead of going out 1 each side, now I go down 2 each side and plot a point. And now from here, I go down 1, 2, 3, 4, 5, 6, because before I was only going down 3 to plot those points. Okay, so 6 times 2, that's, 3 times 2, that's 6. So that's my now distance. And then the next distance would be 10, which I don't have. 1, 2, 3, 4, 5, 6, right? So I don't have more space to show this next distance. But how do I know that? Well, look, we went from up 1, right 1, to from here, up 3, right 1, and then up 5, right 1. And then you have that match on each side. So this really narrowed and flipped me. So it really narrowed up and flipped me over. So let's describe what that would look like in actual equation notation and in, because they gave us our function notation, right? So this would be if -2, we're multiplying by -2, f of x, and then we're adding 4 at the end. What that says to me as my x squared is a -2 in front of my x squared and adding 4 at the end. Let's see if that's what we get when we put that in here. I don't think I have a purple, so let's just use magenta. We'll do -2 times x squared plus 4. And when we press graph to see it, we're up here. Then if we look second in graph to be on our actual table of points, okay, so there's your 0, 4, which we predicted was going to be our vertex, and then out on each side, we're out 1 but down 2 on each side, and then look, we're out 1 more but down 6. And so that's how it narrows up, is it's multiplying those values by 2. Right, it's multiplying those original values by that -2, and so that's where the narrowing has occurred. So there you go. And notice a lot of times we give you a graph as optional so that you can show the changes that you would be making as you're going. All right, so this really is the key, is understanding what each of the movements describes for our quadratics. Now, since we are in the quadratic functions unit, we are focusing all these movements on quadratics. But these function movements and these function notations are exactly the same for any function I'm trying to move in any of these directions. So anytime I want to flip a function over, I multiply the front by -1, whatever that may be, whatever function I'm trying to do that with. Okay, and so whenever I want to move to the, let's say, the right 3, then I am subtracting 3 on the inside of whatever parentheses we are indicating. And since this is a quadratic, the x squared is the parentheses that we are looking at. So the squared parentheses is how I move left and right. If I say wanted to add 4 to the end of any function, I would go to the very end and I would just add a 4 at the end of whatever it is. And that's going to move me up 4 in my y's. And so understanding each of these types of function notations and how they really are the same with every single function, that is really a clutch thing for anyone who's working with function notation. Okay, so anytime you're working with that function notation. Okay, I would, if I were you, as you're going through this, keep the parent function of f of x equals x squared or y equals x squared, write ny1 in your graphing calculator as you're making these changes. I would also have my graphing calculator with me so that I could verify any of these changes that I was making. So I'm checking myself using my graphing calculator, just like I did here. Okay? All right, my fine friends, I will be seeing you after this. This is the end of chapter 11, so now we're starting to get ready for our chapter 11 exam. If you have any questions, as always, please let me know. And I will see you next for our graphing exponential functions unit. So we're moving on from quadratics into exponentials next. All right, everyone. See you soon. Bye.